All right, people, welcome to the second lesson for Unit 7, or Unit 4. We're in Topic 7, which is about trigonometry. We're going to start off by looking at our essential question for this unit, for this lesson. And our essential question is, how can we extend the trigonometric ratios to angles greater than 90 degrees? So hopefully, if you think you can remember back to last week when we talked about the first lesson out of Unit 4 from Topic 7, all the angles that we were looking at were angles that were less than 90 degrees. They were all acute angles. So the triangles that we looked at, we were focusing on, there was a couple special ones. We talked about 30, 60, 90 triangles, where one of the angles is 30 and one of them is 60, and then the third one is obviously 90 degrees. And another special triangle called a 45, 45, 90 triangle, where two of the angles are 45 degrees and then the third one is 90. But the common theme of last week's lesson was that we were looking at triangles where the angles were acute angles. But we're going to get into today's lesson is angles that are more than 90 degrees and how can you work with them. So we're going to jump into a warm-up first. And once this loads, our question says, a bug is placed at the point 1, 0 of the coordinate plane shown. And then it starts walking counterclockwise along a circle with a radius of 1. So you can see right now in the graph that's here, this bug's not actually at the point 1, 0. So I'm going to drag the bug down to the point 1, 0. So now the bug is sitting at 1, 0. It's on the x-axis. And this bug is going to walk counterclockwise. So counterclockwise would be walking up. So if we drag this thing, you can see the bug's walking, walking, walking. And, eventually it walks all the way around the circle and it gets back to where it started from. So that's the visual of what's going on in the problem. Part A says, how can you calculate the distance along the circle that the bug has traveled? So hopefully you remember from much earlier in your life that when you have a circle and you want to travel the distance around it, that it's this formula. Circumference is 2 pi. Let me see if I can pull up the actual symbol. Let me get some pi in here. Geometry? Nope. Trigonometry? Ooh, here's a pi. So back up here. It's 2 pi times r. Let me put a times in here, times r. That's always your circumference of any circle. And what is our radius on this circle? Well, hopefully you can see that it's 1. So I'm actually just doing 2 pi times 1, which is just 2. And let me get my pi symbol back up here. 2 pi. So how can you calculate the distance along the circle the bug has traveled? Well, it's always 2 pi r. And for us, because our radius is 1, the distance is going to be 2 pi. How can you determine, so that's the answer to the first question of part A. The second question for part A says, how can you determine the measure of the central angle? So a central angle is, let me put this bug back over here somewhere in first quadrant. So the central angle is this distance from the x-axis up to this gray line that represents where the bug is. So the central angle is this angle inside here. And that angle is actually going to, I don't know if you can figure this out, if it's super intuitive or not, but if the bug is starting back here, when it starts at 1, 0, there's no distance at all between the x-axis and how far the bug has gone. It hasn't traveled anything yet. So right now, the central angle is 0 degrees. But as the bug moves, it's getting a bigger and bigger angle. Maybe you can see this looks like it's about halfway between the x-axis and the y-axis. And you should know that this angle from the x-axis up to the y-axis is 90 degrees. So if I'm halfway, that would be 45 degrees. If I go all the way up to the y-axis, oops, right, maybe get a little bit closer. I don't think that's still perfectly on the y-axis, but you can see that that should be 90 degrees. It's 1/4 of the circle, and a full circle is 360 degrees, and 1/4 times 360 is 90 degrees. So what you should be able to see from that is that each of the quadrants on the graph, 1, 2, 3, and 4, represents 90 degrees. So the angle that we have here, just need to move this around. So as the bug's moving, this angle that it's moving is just some fraction of 360. So the central angle is some fraction of 360 degrees. And it's the amount that the bug has traveled. So I'm not sure, you don't really know what that is, but it's always going to be less than 1, because if it's traveled the whole way, then it's going to be 360 degrees over 360 degrees, and that's going to be 1. If it hasn't traveled anywhere at all, then it's 0 degrees over 360, which is 0. So this is always going to be some fraction, out of, it's going to be, the lowest it can be is 0, and the biggest it could be is 1. But anywhere, if you're in the first quadrant, let me put the bug back in first quadrant. If you're in first quadrant, the bug, the central angle is going to be somewhere between 0 and 90 degrees. If you go somewhere in the second quadrant, the central angle will be somewhere between 90 and 180. If you're in the third quadrant, it'll be somewhere between 180 and 270. And then if you're in the fourth quadrant, it'll be somewhere between 270 and 360. So that's part A. If we look at part B, it says when the bug has traveled 1/8 of the way along the circle, how far has it traveled? So let's start off with that. First off, we know that the total distance around this circle that we're looking at is 2 pi. That's from part A, because it's 2 pi times the radius, and the radius was 1. So if we've traveled 1/8 of 2 pi, what does that equal? Well, 2 over 8 reduces to 1/4. So this becomes just pi over 4. So that's the distance it's traveled. And obviously there's no units here. They didn't tell me if this is inches or centimeters or feet or anything. So you could just say units. It's pi over 4 units. That's the distance along the circle it's traveled. And then what central angle does its path travel through? So we know that the distance it's traveled is pi over 4 units. And that actually is also the angle that it's traveled through. So let's say pi over 4 units is the distance that the bug has traveled along the circle. But it is also the measurement of the central angle. And the thing is, you don't really know what that means yet in terms of pi over 4. But if it's traveled 1/8 of the way around the circle, let's move the bug back. So this would be right here. That would be 1/4, because that's 1/4 of the circle. So 1/8 is half of 1/4. So let's go back and say, let's cut this pi over 4, or this quarter of the circle. Let's cut that in half. So now this is 1/8 of the whole circle. If you can imagine this line right here, this gray line, cutting the first quadrant in half, if you put one of those lines also in quadrant 2 and 3 and 4, then you can see the circle gets split into 8 equal parts. So right now the bug is at, it's traveled 1/8 of the distance around the circle. So this is an angle that's pi over 4. But visually, you should also be able to see that we're cutting 90 degrees in half. And so that's 45 degrees. So we can say that the bug has traveled through a central angle of 45 degrees. Okay, let's see, we have a part C here. What are the distances shown, traveled, and the central angles when the bug has traveled 1/6 of the way around the circle and 4/5 of the way around the circle? So for both of these, again, what you're going to want to do is take 2 pi and multiply first by 1/6, and that's going to give you 2/6 reduces to 1/3, so that's going to give us pi over 3. For the first one. And for the second one, actually I'm going to come back over here, put a comma. We're going to do 2 pi. This time we're going to multiply by 4/5. And 2 times 4 is 8 over 5. 8 over 5 doesn't reduce, so our answer is just going to be 8 pi over 5. So those are the 2 answers for part C. And I totally understand that pi over 3 as a distance and 8 pi over 5 doesn't make the most sense to you right now. But we're going to get to that later on in this lesson today, explaining what that actually means in a way that is going to have more meaning to you. It's not really clear right now, but it's going to be clear by the end of the lesson. So we're going to jump over to the examples now. Okay, so now we're looking at example 1. And example 1 says that we need to find the measure of an angle in standard position. So the first thing that we're going to do, well, the question says, what is the measure of the angle shown? And you can see that we have an angle here, and I'm going to draw on here and add in, oops, let me make this a little bit heavier so you can see it a little bit better. Our angle theta is this angle that's in here. And before we get into actually solving this, we're going to review a little bit of the special triangles that we talked about in last week's lesson, which are the 30, 60, 90 and the 45, 45, 90 triangles. So we have, first off, we're going to talk about, this is the 30, 60, 90, and this angle up here is 30 degrees, and this angle down here is 60 degrees. And I'm just going to draw the 45, 45, 90 first, but I'm not going to talk about it yet. This is 45, and this is 45 down here. Okay, so last time when we talked about the 30, 60, 90 triangle, we saw that the shorter leg, which is down here, is always x, that the hypotenuse is always twice x, and that the other leg, the longer leg, is x times the square root of 3. And that relationship always works for every 30, 60, 90. It's never going to change. It's always going to be that. So then now also for the 45, 45, 90, we talked about that the legs are the same length because this is an isosceles triangle. So if one of them is x, the other one is also x. And the hypotenuse is always x times the square root of 2. So we're going to keep these relationships in mind when we're working through this problem here. So the first thing that you want to do when you're thinking about the angle that's shown is we're going to define some stuff. So this problem is going to be heavy on definitions and setting you up for the content of the lesson. Anytime you draw an angle that's on an XY axis, you always have to start from the X axis. You can see down here that we have this red line along the X axis down here. This is always called the initial side. And if the reason where this word comes from, initial, if you don't already know what the word initial means, don't think about like your initials, like my initials are JW. Don't think about that. Think about what the word initial means in terms of like if you initiate something. And if you don't know what that means, lots of English words come from Latin. There's lots of English words that come from, German and Norse and other languages as well. But an initial is one of the words that has a root in Latin. And lots of you guys speak Spanish, and Spanish also has its roots in Latin. So the comparison I'm going to make here, if you think about like what word in Spanish looks really similar to initial, you might think of the word iniciar. And hopefully you know what iniciar means in Spanish. It means to initiate or to start something. So the initial side is where you start from every time you draw an angle on the XY axis. And then the ending point where you have this point up here, this line up here to get to that point, always starting from the origin, that side is called the terminal side. And again, I'm going to relate this to Spanish, but it probably also relates to Latin. I just don't know Latin, but I know Spanish. So if you think about a word in Spanish that looks very similar to terminal, that's also a verb, kind of like iniciar is a verb, hopefully you can come up with the word terminar. And terminar means to finish or to end. So the terminal side is where you end. The initial side is where you start. So this is your starting side, and this is your ending side. And then between those two things, you're going to start from the x-axis, and you're going to draw an arrow tip that goes to the terminal side. And that's how you form an angle when you're drawing angles on the xy axis. So they want to know, what is the measure of the angle that we're looking at? So in order to do that, what you need to do is take your terminal side, that coordinate point that's up here, and you're going to draw a line straight on down. Sorry, that wasn't straight. Let me fix that. You're going to draw a line straight down to your x-axis. And you can see that when we do this, if I finish this off, then I have formed a new triangle that's in the second quadrant. I've got this triangle that's over here. And I'm going to take that triangle and then just draw it off out here to the side. Based off this coordinate point here, you can see that we have moved -4 in the x direction. If we're starting at the origin, we've moved 4 spaces left. So we're going to put a 4 down here at the bottom. And we're not putting -4 because when you're moving distances, you can't move a negative distance. You can move to the left, but you can't move negative distance. So this is 4 spaces left. So this bottom side has a length of 4. And our y value is 4√3. So that's the longer leg. That's the y value on this triangle. And then we have this unknown side, the third side. And hopefully you can see, because it's across from the right angle, that it's our hypotenuse. And there's a couple ways that you can solve your hypotenuse. Hopefully you can see that based off of the 30, 60, 90 triangles over this triangle over here, that if our bottom side was x, so if I say that x is 4, that the longer leg is always x times the square root of 3. Well, does that fit over here? That sure looks to me like it's x times the square root of 3. And so because both of these two sides fit, the hypotenuse is going to be 2 times x. And for us, that's 2 times 4, which is 8. So we know that this triangle here fits a 30, 60, 90, which means that this angle down here has to be 60 degrees. This angle up here has to be 30 degrees. So that's one way that you can figure out the hypotenuse. If you don't know, if you don't know that it fits a special triangle of 30, 60, 90 or 45, 45, 90, then you can always try the Pythagorean theorem. That will always work. I'm not going to do it here, but if you see a triangle and it doesn't fit one of the special triangles, then do the Pythagorean theorem. Okay, so now that we know our angle in here is 60 degrees inside this triangle, first off, this angle in here, let me switch to another color. This angle in here is called a reference angle. And the reason it's called a reference angle is because it helps you refer to your angle theta, but it's not actually a part of angle theta. So if I draw a little picture down here, this is going to represent my x-axis and this is going to represent my y-axis. And I know that my angle theta is somewhere over here. So angle theta is that, and that's how I get to it. But then I also have my 60-degree angle that's over here on this side. So you want to figure out theta. So you're going to think back to your geometry knowledge, and whenever you have a straight line, geometry told you that a straight line is 180 degrees. So if this total down here, this whole thing from here all the way over here, if that's 180 degrees and this part is 60 degrees, well then what is this part? Hopefully you can see that that's 180 minus 60, which is 120 degrees. So when they ask what's the measure of the angle shown, your answer is 120 degrees. All right, now we're going to check out example 2. So example 2 says, what's the reference angle for a 130-degree angle? So the first thing I probably want to do is edit my picture. Okay, the first thing I'm going to do is draw a coordinate axis. This is my x-axis, this is my y-axis. And I know that, again, if this is where I start from, that's 0 degrees, that a full circle is 360. So if I split it into 4 equal parts, up here would be 90 degrees, this would be 180 degrees, this would be 270 degrees, and then back here again is 360 degrees. So it should be obvious to you that when I draw a 130-degree angle, that I'm going to be somewhere over here. That I start at my initial side, I go to my terminal side. Let me draw an initial side for you. That's my initial side. That's my initial. This is my terminal. And so 130 degrees is our angle theta in here. And we want to figure out the reference angle. So again, to draw the reference angle, you're just going to take a line and draw straight down to your x-axis. And now you've created this triangle right here. And your reference angle is this angle theta that's in here. So again, just like we looked at in example 1, a straight line is 180 degrees. Your green section here is 130. So that means theta has to be 50 degrees. And that is your reference angle for a 130-degree angle. Okay, now we're going to check out part B of this example. Part B wants to know what is the reference angle for a 210-degree angle. Let me try, see if I can put this square grid. Ooh, this is awesome. Okay, so I have my square grid on here already. This is going to be my y-axis. Here's my x-axis. We know that this is 0, 90, 180, 270, and then 360. So let's pick a color. Let's go with, I don't know, purple this time. We're going to draw an initial side along the x-axis. 210 is somewhere down here in the third quadrant. I think it's probably closer to 180. It's about 30 degrees beyond 180. So this is my terminal side, and then here's my angle. So this is initial. This is terminal. So now to find out my reference angle, you always draw your reference angle to the x-axis. So you start from the terminal side and you draw to the x-axis. So you've created this triangle right here, the yellow triangle. And your angle theta is always between the terminal side and the x-axis. So your reference angle is always between the terminal side and the x-axis. Always, always, always. So if you know that this angle theta in here is a 200, well, I didn't label it theta. Theta is not 210, but this purple angle is 210 degrees. And you can see that 210 goes to 180, and then it goes a little bit past 180. How far past 180 is it? Well, here you're going to do 210 minus 180, and you get 30. So this angle theta in here, let's change back to yellow, theta is 30 degrees, and that is your reference angle. So anytime you're in quadrant 3, the angle that you're given minus 180 will give you your reference angle. And let me change colors and go to blue. If I had an angle up here, like we did in part A, I believe part A we had something up here, and this was 130. To get that, we found that it was 50. So in quadrant 2, it's always your given angle plus the reference angle is going to equal 180. Or you can say 180 minus the given equals the reference. If we're in, let's go red for quadrant 4. If we're in quadrant 4 and you have some angle that comes around, boom, here. Let's say that my angle is 240. Oops, not 240, because 240 has to be bigger. We have to be bigger than 270. Let's say our angle is 315 degrees. So if I drew my reference angle for this, that's my terminal side. My reference angle would have to take me back to the x-axis. You can see that this full circle, the x-axis, is now 360 degrees. So for quadrant 4, you're going to do 360 minus your given, and that's going to give you your reference. So there's 3 different formulas that you can use to figure out what your reference angle is. So if you're in quadrant 2, just to summarize this, if you're in quadrant 2, you're going to do 180 minus your given, gives you the reference. If you're in quadrant 3, you're going to do the given minus 180 to get the reference. And if you're in quadrant 4, you can do 360 minus your given to get the reference. All right, let's go back and look at part C for this example now. Part C says a reference angle is 45 degrees and its terminal side lies in quadrant 4. So let's draw some axes. Okay, let's draw a reference angle of 45 degrees. No, I don't really like that. I don't think I drew it well enough. Okay, so back up there, my reference angle is 45 degrees. This is the, let me change colors for this so we don't get too confused. This right here is your terminal side. And remember, always your initial side, it has to be the x-axis. Okay, so the question is what? So let me draw my angle also. So my angle, boom, goes like that. That's theta. What are the possible positive and negative measure angles for this angle? So if you think back to what we just said for part B, because I'm in quadrant 4, I can do 360 minus the given angle, which will give me the reference. But I don't have a given angle this time. This time I have the reference angle. And I know that that's 45 degrees. So if I say 45 degrees over here, 360 minus the given is 45. To move the given over to the right, I'd have to add it. And to move 45 over to the left, I'd have to subtract it. So this is going to say 360 minus 45 is going to be your given angle. And 360 minus 45 is 315. So that's one way you can solve for the angle. And notice that's a positive measurement. So that's one of your solutions for this problem. However, you should have noticed that every time I drew an angle so far today, that I've always been moving counterclockwise. Boom there, counterclockwise, maybe around here. I'm always going counterclockwise. So anytime you move counterclockwise on a graph, you have a positive angle. But you know there's two ways you can move around a clock. You can move counterclockwise or you can move clockwise. So right now your intuition should be telling you, if counterclockwise is positive, that clockwise is negative. So what if I did this angle, but I moved in a clockwise direction instead? So now I'm going to draw my axis again. I'm going to draw the same reference angle. Boom, still 45 degrees. So what happens if I move clockwise from the x-axis down to my terminal side? Well, it should be really obvious. This angle in here is the 45 degrees. But because I'm moving in a negative direction, I can see this has to be a negative 45 degree angle. So if you took, so first off, our negative answer, boom, is negative 45 degrees. Our positive angle was 315. What do you notice about the positive angle and the negative angle? So let's look and see. If we took 315, if I took, let's say, the absolute value of that, and I added the absolute value of the negative, the clockwise and the counterclockwise direction, what do we get? Well, absolute value makes everything positive, so 315 and 45 gives me 360, and it gives you a full circle. And that should always work out. Your positive measurement and your negative measurement, when you take the absolute value of them, should always add up to 360. And if they don't, then you didn't do your problem correctly. One third way, so we've learned two ways. This is your first way to think about it, moving counterclockwise. Your second way is moving clockwise. That's two ways to think about it. There's actually a third way to think about solving this problem also. And you might, this picture over here on the left, this thing that I drew, it should kind of look a little bit interesting to you just because it has all these, curved lines around it. Maybe you wonder what happens if I start at my initial side and I go a full circle around, but then I just keep going. Can you see each time? Let me erase that because that picture is way too busy. If I go this black line, I'm just going to trace this. If I go all the way around here, I've gone 315 degrees. Well, what if I pick up again from this terminal side and then I make another full circle? I got back to where I started. What if I did it again? I get back to where I started. If I do it again, I get back to where I started. So when every time you make a full loop around a circle, you're doing 360 degrees. So this angle could also be considered 315, which is our positive measurement, plus some multiple of a full circle, 360 degrees. So K is just how you say some constant. So if K is 0, 360 times 0 is 0, and that just gives you 315. But if K is 1, then you have 315 plus 360, which just puts you back in the same spot. So another way you could talk about this is 315 plus 360K. And then technically, if you want to think about the negative direction also, you could say it's negative 45 plus 360K. But if you said that K was negative 1, so 360 times negative 1 is negative 360, then you'd have 315 minus 360, and you'd get negative 45 anyway. So this thing technically doesn't really need to be said. It's really just this first way in blue that's really important. So we've got 3 total ways that you can talk about any angle. And you can always talk about any angle that you're given in 3 different ways. All right, now let's jump over to our next concept, and this concept is the unit circle. So the unit circle is something that's really, really, really important. It's going to come up a lot for you guys next year in units 3 and 4 for pre-calculus. It's going to come up if you take the trigonometry class, if you take probability in trig. Ooh. My screen share stopped. Okay, we got it back. So like I was saying, the unit circle is going to be covered in units 3 and 4 of pre-cal. It's going to be a major focus if you take the trigonometry class. For all of you guys who are going on, if you're sophomores now and you're going on to take calculus your senior year, it's going to be an expectation that you know the unit circle, that you have it memorized, that you understand everything about it. This is one of those concepts that's going to come back over and over again, pretty much for the rest of your math career, in a similar way to how factoring quadratics is going to repeat itself many, many times for the rest of your math career. So talking about this concept, the unit circle is a circle that has its center at the origin. That's really important. Center is at the origin, and it has a radius of 1, and that's also really important. So those are like the 2 main features of something being a unit circle. It says, in any right triangle formed with the radius as the hypotenuse, the length of the hypotenuse is 1, which should be really obvious to you. Let's draw in red. Well, let's stick with a different color. Okay, so if the radius is 1, obviously from the center out to the circle, that's 1 unit. Well, if you go from here out to the circle, that's 1 unit. From here out to the circle, 1 unit. Really, any radius that you draw is a distance of 1. So the hypotenuse of any triangle, let me draw some hypotenuses. I'm not sure if that's a word, but if I draw for the hypotenuse, boom, if I draw my reference thing, now I've made this triangle. If I draw one over here, boom, drop it down, reference angle, now I have this triangle. You can see every one of these triangles that this is the hypotenuse, this is the hypotenuse. If I draw this triangle, drop it down, this is still the hypotenuse, this triangle, drop it down, that's still the hypotenuse. That the radius is always the hypotenuse of every triangle that you draw inside of a unit circle. So reviewing back from the first lesson that we covered last week, you know that sine is always the opposite side over the hypotenuse. But our hypotenuse is always 1. So if our hypotenuse is 1 in the unit circle, that means that the sine relationship, the sine of angle theta, is just the opposite side. We know that cosine, come on, red, cosine of theta is the adjacent side over the hypotenuse. But if the hypotenuse is 1, that means that the cosine of your angle is just the length of the adjacent side. And that's what it's saying here and here. Anytime you are on an XY axis, the opposite side is going to be Y. The opposite side is Y, always. And the adjacent side is always X. So that's super important. We're going to come through, and eventually you're going to learn there's lots of important angles as you move around your unit circle. Obviously, we know this is 0 degrees, and this is 90 degrees, and this is 180 degrees, and this is 270. And when we get back here, we're at 360. So you can see that the quadrants, the 4 quadrants, those are important special angles. But there's also angles within each quadrant that are really important. And eventually, you will need to know them. You don't need to know them right now because you're just being introduced to this concept. But eventually, you're going to learn how this works and what this means. So let's go on and check out our next example. So for example 3, we're going to find the coordinates of some point on the unit circle. So we have an angle theta that has a measure of 60 degrees and a terminal side that intersects the unit circle at some point x comma y. So let me draw my axes. Okay, a 60-degree angle. Let's say that's about there. This is our terminal side. We have a 60-degree angle. We're going to drop down to make our triangle. This is a 90-degree angle. And this point right here is some point x comma y. What are, okay, this is on the unit circle, so we know that this has to be 1 unit. The hypotenuse is 1 unit. And we want to know what is x and what is y. So if this angle down here is 60 degrees, that should make it pretty obvious to you that this angle up here has to be 30 degrees. And you can see that we have now a 30, 60, 90 triangle. So I'm going to sketch my 30, 60, 90 off here on the side. And I know my hypotenuse is 1. Actually, I'm not going to put that on there. I'm going to put the relationships that we already know. We already know that the bottom side is x. We know that the hypotenuse is 2 times that. And we know that the longer leg is x times the square root of 3. So if I compare the green triangle to the red and blue triangle that's on my axes, and the sides I know the hypotenuse already. I know this side right here is 1. So I can set up a relationship and say that 2x is equal to 1. The hypotenuse has to be equal to the hypotenuse. And that lets me solve for x. So if I do that, I'm going to divide both sides by 2, and I get x is 1/2. So there's my first answer. What's the value of x? Well, it's 1/2. Now I want to find y. Y, I can see on the red and blue one is just y, and on the green one, it's x times the square root of 3. But right now I know that x is 1/2, so I'm going to do 1/2 times the square root of 3, which is just square root of 3 over 2. So y is the square root of 3 over 2, and that's my answer for y. Answer for y, boom, down here. And that's how you can solve for any x and y. If it's some angle, obviously this angle that they gave you, 60 degrees, led you into one of the special triangles. So right now they're just focusing on the special triangles, the 30, 60, 90, and the 45, 45, 90. They're not getting into other angles that you don't know how to do yet. All right, next example, we're going to check out example 4. Example 4, we want to understand radian measure on a unit circle. Radian here is probably a word that you've never seen before, but you can see that it looks really similar to the word radius. And if you're not sure, that is actually a U. It kind of looked like an O, but it is the letter U, a radius. Okay, so we are going to draw ourselves a circle first on top of a set of axes. That's not a perfect circle. Sorry, it's really hard to freehand draw perfect circles. You know, for any circle, obviously you can see that we've traveled distances around circles so far today, and you know that that's the circumference. And you know that the formula for the circumference is 2 pi r. And what does r stand for? Well, it stands for the radius. And radian and radius, very, very similar concepts. So let's say that we're looking at a unit circle here. So let me label on my circle that from here to here is a distance of 1 unit. And that makes this a unit circle now. So my radius is 1. So what's the circumference of a unit circle? Well, it's going to be 2 pi times 1, or just 2 pi. So a full circle, we go all the way around here. If we're talking about degrees, you know it's 360. But now you know in radians, it's 2 pi. So the radian measure of an angle, so if a full circle is 360 degrees, then some angle, let's say that's, I don't know, a 90-degree angle. Well, 90 degrees is 1/4 of your circle. Well, what's 1/4 of 2 pi? So if you did like 1/4 times 2 pi, you would get pi over 2. So pi over 2 is the radian measure of a 90-degree angle. So anytime you're talking about an angle, you can give the measurement of it in degrees or in radians. And that's what a radian measure is. All right, part B of example 4. How can you use the radian measure to sketch an angle? I think we kind of already did this, but let's throw up some axes and let's draw an XY axis on top. And let's come up with, I don't know, let's come up with a angle called pi. So I'm going to draw a unit circle again. That is the ugliest circle I probably could have ever drawn. We're going to say this is 1, that this is 1, that this is -1, and that this is -1. So you know that a full circle in degrees is 360 degrees. You know that a quarter circle is 90. You know that half a circle is 180. 3/4 of a circle is 270. But what on earth is pi? So the full circle, let's go back and think about radians. If you're at the beginning, this is 0 radians. If you have a full circle, then it's 2 pi radians. Well, what's 1/4 of 2 pi? 1/4 of 360 is 90. What's 1/4 of 2 pi? Well, it's pi over 2, because we just did that in part A. What's 1/2? Because half a circle is 180 degrees. What's 1/2 of 2 pi? Well, half of 2 is 1, so this is pi. What's 3/4 of 2 pi? I'll do that over on the side. 3/4 times 2 pi. Well, 2 over 4 reduces to 1 over 2. So this gives us 3 pi over 2. So 270 degrees is also 3 pi over 2 in terms of radians. So if you know the radian measure and you sketch your triangle out here with 0, pi over 2, pi, 3 pi over 2, and then 2 pi, if you think about it like that, then it's really easy to draw the radian measure. So if I want to draw an angle with a measurement of pi, I'm going to start on my initial side. Pi is over here, so I'm going to go all the way over here, and that's my terminal side. So this is my initial, this is my terminal, this is theta, and that's an angle of pi in radian measure. All right, let's move on to example 5. Example 5, what we're going to do is practice converting between degrees and radians. So how do you do that? So let's say that we have, well, let's just draw our axes first. So let me put the axes back up here. Let me draw this. Let's draw a unit circle, and I'm going to try to draw it a little bit better this time. Maybe that's a little bit better. We're going to say that this is 1. So now we have a unit circle. And we know, let's do red for degrees. This is 0 degrees, 90 degrees, 180 degrees, 270 degrees, and then back here is 360. And we're gonna do blue for a radian measure. This is 0 radians, this is pi over 2 radians, this is pi, this is 3 pi over 2, and then back here is 2 pi. So you can see from this that we have this relationship that pi over 2 is equal to 90, and pi is equal to 180, and 3 pi over 2 is equal to 270, and 2 pi is equal to 360, and obviously 0 radians is equal to 0 degrees. So converting between these involves a unit conversion, because on the left side here, we have our measurements in radians, and on the right side, we have our measurements in degrees. So when you convert from radians to degrees, you can see that the pi is going away every time, and that we're coming up with some number. The way you want to think about unit conversion here is the same type of thing that you did when you did unit conversion when you were a kid. So let's say when you were a kid, you had 1 foot, and your teacher was like, well, how many inches are in a foot? And you say, oh, I know that there's 12 inches in 1 foot. So let's say that Mr. Woodring is 6 feet 3 inches tall. So how many inches total is that? Well, you can obviously take the 3 from the 3 inches and know that I'm at least 3 inches tall, but then how many inches are in 6 feet? So to do that, you would say 6 feet, and I'm going to multiply by 12 inches are in 1 foot. And then I have feet in the numerator and feet in the denominator, and they cancel out. So I just do 6 times 12, and I get 72 inches. And I know it's inches because inches is the only thing that's left on the left side. So I'm 72 inches plus 3 inches, and that means I'm 75 inches tall. And that's how you did unit conversion back when you were a kid. Well, there's a similar conversion factor. Like you see this right here is your conversion factor. There's 12 inches in 1 foot. There's a similar conversion factor for going from degrees to radians or radians to degrees. Anytime you want to move from radians to degrees, you're going to multiply by 180 divided by pi. So if I started with pi over 2 and I multiply by 180 over pi, you can see that the pi's cancel out, and 180 divided by 2 is 90, and that's how I got the degrees. If I have pi and I multiply by 180 over pi, the pi's cancel, and I'm left with 180. If I have 3 pi over 2 and I multiply by 180 over pi, the pi's cancel again. 180 over 2 is 90, and 90 times 3 is 270. So you can see that every time you multiply by 180 over pi, you can convert between radians and degrees. But there's another way you can do this. What if you're going from degrees to radians? So degrees back to radians. Well, the conversion is just the opposite. So to go from degrees to radians, you're going to multiply by pi over 180. So radians to degrees, you multiply by 180 over pi, but degrees to radians, you do pi over 180. So let me say if I had, I don't know, a 60-degree angle and I want to go to radians, then I'm going to do 60 times pi over 180. 60 over 180 is 1 over 3. So this is pi over 3 radians. And that's your conversion factors. Okay, let's check out part B of example 5. We're going to do a couple conversions in this one. The first conversion that we're going to do is pi over 7. So we have pi over 7, and this one we need to multiply by 180 over pi. We have 75 degrees, and this one we're going to multiply by pi over 180. And I can come up with those super easy because I know every time I do this, if I'm starting with pi's in my answer, I need to get rid of the pi's. And if pi's in the numerator, the only way to get rid of it is to multiply by it within the denominator. So I know this has to be 180 over pi in order to cancel my pi's out. Let me do that in a different color. So my pi's cancel. And this is 180 over 7 degrees. And I don't, like, obviously this doesn't divide well because 7 doesn't go into 180. But if you did that on a calculator, well, let me see if I can do this in my head. 140 over 7 would be 20. So 180 is 140 plus another 40. So if 140 over 7, this part would give me 20 degrees. 40 over 7, that's 35 and 5/7. So that's 5/7 is 0.728. So this would be about 25.7 degrees. And then if I had 75 degrees and I want to convert that into radians, I know I need to use pi over 180 because I need to have a pi in my answer. 75 over 180. I don't think that's going to reduce super easy, but I know each one is divisible by 5. If I divide that by 5, I get 15. If I divide that by 5, I get 40 minus 4, 36. So I get 15 pi over 36. And I don't, ooh, that does reduce a little bit more. I can take a 3 out of each of these. If I divide that by 3, I get 5. If I divide that by 3, I get 12. So my final answer is 5 pi over 12 radians. So that's your conversion. Just remember every time you either have to, if you're going from radians to degrees, do your 180 over pi. If you're going from degrees to radians, it's pi over 180. All right, last example, example 6. We have an application. It says that NASA is tracking a satellite traveling in a circular orbit above Earth. It can only be tracked while it orbits through a pi over 6 angle. Let's try to draw a pi over 6 angle. This is 0 radians. This is pi over 2 radians. Pi over 6 is like 1/3 of that. So let's go, I don't know, about there. And we're going to call this theta is pi over 6. So my angle, I'm starting at my initial side, which is here, and I'm going up towards my terminal side. So that's the picture that's going on here. The radius of the Earth is 6,400 kilometers. What is the distance that the satellite travels while it is being tracked? So they tell us over here that the satellite is some distance above the Earth's surface, which is obvious because, you know, satellites don't just sit on the Earth, they go up in space. So if we think about the origin is like the center of the Earth, then we know the radius of the Earth is, I'm going to change colors just so this is a little bit easier to see. Let's say this is, I don't know, the end of the Earth right here. So that's 6,400. And then we're going to go another distance out to show that the satellite is traveling up into space. So the combined radius is 6,720 kilometers. They want to know what is the distance that the satellite travels while it's being tracked. Well, the satellite travels along, you know, some portion of a circle. And, you know, I'm not drawing a perfect circle, but this is the distance that we are traveling. So what we need to do here is take our pi over 6, our angle measurement. Let me change back to black. We're going to take our angle measurement and we're going to multiply by the radius that we're given. And that's going to give us the total distance that this satellite has traveled. So I do actually know that 6 goes into this number 6720. And I know I'm going to have a pi left over. I know my distance is going to be in kilometers. 6,000 over 6 is 1,000. 720 over 6 is 120. So this is 1,120 pi kilometers. And that's the distance that the satellite has traveled. Obviously, first off, I will say I'm perfectly cool with you leaving your answers, and I would actually prefer you to leave your answers like this with pi in the answer. But you're going to see some problems where they say round to the nearest whatever. And if they do that, what they want you to do is take the number pi on your calculator, type pi, and then times 1120. You know pi is like 3.14, but I don't ever want you guys to use this. This is a big no-no. Don't say it's 3.14 because you're ignoring all the other decimals that come after 3.14. I want you guys to actually use the pi button on your calculator if you ever come into a problem where it says round to the nearest whatever. Use the actual pi button. You can use all the decimal places. Okay, so that's example 6. Just as a summary real quick, we're going to look at the things that we've talked about today. So this is just your concept summary for everything. First off, standard position is your angle theta that's in this picture right here. Your initial side is always along the positive x-axis. The terminal side is always where your angle ends up, where it ends. You have your starting side and your ending side. The reference angle occurs when you take a straight line from the terminal side down to the x-axis. Then we have degrees and radian measurements, and you can see a bunch of different angles that they've given you here and the conversion factors. So use these concepts, use the examples that we've had to work on your assignments for this lesson. Okay, people, I know this lesson went a lot longer than our first one. I'm sorry about that, but there's a lot of stuff to cover in here. Again, hope you guys are staying safe. Everyone, obviously, you have to go outside with masks now when you go to a store or anything. Be smart about it. Make sure you guys get outside. Enjoy the weather when it's nice outside. Don't stay cooped up inside all day. If you're an athlete, you should still be working out. Try to stay in shape for next year, the summer. Don't just sit on your couch all day. Don't play video games all day. My internet came back, so I'm recording at home. It's wonderful. I much prefer being at my own house than my parents' house. But yeah, that's our video. Hope you guys have a good week.